Um, Welcome to SharkNet General Interest Seminar, and today I'll be talking about the computing in arbitrary position. Rather than give you a thorough introduction to arbitrary or multiple position for computing, I will just walk through some examples and show some pointers to the audience so that you can spend your spare time to look for more information. So let's get started. First, let's have a quick review on the floating point operations and see why higher precision is wanted sometimes. So first, let's take a look at this simple data representation example. I have the code in C and the Fortran side by side. So what we do here is we define the A, B, C as three floating point numbers, variables, all in single position, 0.5, 0.1, and 0.25. And we just simply print them out, A, B, C. And as you can see, A and C are in exact the value that we define, while B, which we set to 0.1, is not what we want. We have something extra after the decimal point. So, consider a simplified floating point number representations. So here we have a two digit, the base 2. And the following are all the positive numbers. If you do a quick math, you can figure it out. Both D1 and D2 will have the possibility of a 1 and a 0 and a 1 and a 1. So for this representation, simplified representation, we have a finite number, a set of finite numbers, and there are gaps in between, and they are not evenly distributed on the x-axis. So what that means is, even before we do anything, we already have lost the accuracy due to the limit in the floating number representation. And we can imagine that during the computation, further inaccuracy will occur, and due to runoff error. So some people use a double position or quad position, or even higher position whenever allowed, in order to obtain the accuracy desired. So there are a couple. There's another example: the common mistakes. So when some people do the floating point comparison, the fact is this may never happen. So you have two variables A and B. If you want to test whether A is equal to B, this might never happen, because the floating point representation internally is stored. Okay. So either the condition is never true, or the results, when you do something inside this if branch, the results are system dependent, which will make your program unreliable. So the correct way of doing this would be, instead of comparing whether A is equal to B, you test whether the difference between A and B is within a given tolerance that you define. For example, if the difference between A and B is less than 10 to the power of -6, for example, then you will treat it as effectively the A and the B are equal, and then you can continue. And this way, you can ensure that the accuracy in your computation is met. More examples here. So 0.5 in a binary representation, 0.5 can be represented exactly. However, 0.1, this decimal number, 0.1, is converted to an infinite sequence, okay? So when converted back to the decimal representation, we see when we set a b equals to 1, then we will have extra numbers after this decimal point, unexpected. So some observations and the facts. So if you set a small number, 0.001, and you add 1,000 times, if the A is in a single position, and you will see the answer is not 1, but instead 0.9999, and because of the runoff. And this can be fixed by using double position, because you will have a more reliable digits after decimal point. An important fact to keep in mind is the summation on any computer with a floating point arithmetic. Summation is not associative, which means if you have three numbers, for example, you add them together, you add A and B first, and then you add C. The result will not be the same, not necessarily the same as you add a B and a C first, and then add to A. That's number one. And number two, even in the double position, if you add a small number, 0.0001, and I think there's a 16 zeros after, or 15 after decimal point, the result is 1. Just because the limitation of the floating point number representation. A quick review on IEEE, a floating point arithmetic or storage. For integer, the regular integer, 4 bytes, the integer, we have 32 bits and 1 signed bit. So what is the largest assigned integer? You can calculate it. And for single position, a floating point of 4 bytes, 32 or 32 bits, and there's a 1 signed bit, a one signed bit, and 8 bits for the exponent, and the 23 bits for the mantissa or the significand. And this will give you about 7 significant digits. Okay. And for double position, the IEEE standard uses a 64 or 8 bytes or 64 bits. It has a 1 signed bit and 11 bits for the exponent and the 52 bits for the mantissa or significand. And this will give you roughly 15 significant digits. Okay. Now, this is actually a real example that we encountered from a user. So what happens here is a variable A is defined, which is 10 to the power of 10, very, very small. And then there's an if branch. It says if A is less than 0, that's A could be anything fairly small, and not necessarily this. If A is less than 0, then we add a 10 to it and then do something. For example, you do something, what is if there's a division or something, and this could be problematic because A here, when A is a small and added, a big number is added to A, the result is that number, not the A anymore. The result is a 10. So the problem is A, afterwards, A is 10, and rather than 9.99999, okay? And this could cause a floating point exception in that user's code. So in general, so if you have a very tiny number and a very huge number, if you add them together blindly without thinking, that could make your code problematic, and the result can be unexpected. And here is, this is actually one of the many extreme examples in this article, Numerical Monsters. Okay, so what we see here is a smooth curve. This curve is the exponential function e to the power of x times a log 1 plus e to the power of a negative x. So what it should look like is at the 0, the function goes from here and quickly asymptotically approaches 1 forever. But somehow, after x is greater than 30, the curve starts oscillating. And then between a 35 and 40, it suddenly drops and flats out to 0 and all the way forever. This is an artifact of this curve due to the floating point operations. Okay. So some facts, and we'll come to this this curve later on. Some facts and needing higher precision. I just list them all here. For example, base conversion. Okay, a 32-bit format needs 126 bits. 64-bit format needs 752 bits, and so on and so forth. And the correct rounding, you will need a higher precision. And the vector inner product, accurate to the next to the last digit. Why vector inner product really matters? Because when you do a vector inner products of two vectors, essentially you're just adding the product of elements by element. Okay, and so you have a summation. And if you want to have the accuracy next to the last digit, then you will need a higher position, especially when the size of the vector is really large. There's some science and engineering applications where higher precision rather than 17 digits, that's what the double position will give you after a decimal point are wanted. And also, mathematical reasoning or proof, sometimes they're called experimental math, would expect the extremely large number of digits. For example, 500 digits at the least in computing determinants of some matrices. Some examples of application, just listed over here. Supernova simulations, climate modeling, and many other applications. I just listed over here. For those who are interested, you can take a look at the some of the applications. Okay. So now let's have a look at the languages and the packages that support a higher position. So here, let's take a look at the example of multiplying two large integers together. On the left, that's a C code, And on the right-hand side, it's a Fortran code. In the C code, I defined a long integer, 3 integers, n1, n2, and n3. And then just enter the 2 numbers, n1 and 2 from command line, and multiply them together and save the result into a variable n3 and print it out. This is a very simple. If you have access to your computer and if you type really fast, and you can try it now and see what result you will get. So I'm trying 2 numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And see what you get with this code. And by the way, this is a wrong code. This C code is wrong. And on the right-hand side, we have a Fortran code. Now, notice I defined the 3 integers, n1, n2, n3. I didn't define as in C as a long integer or whatever. I used the intrinsic function called the select kind, select in kind, and the 36. This function, this intrinsic function takes the argument, which is the exponent of decimal point. For here, that's the 10 to the power of 36. I put a 36 here. And this function will return in a corresponding integer code, whatever internal to the Fortran, okay, to represent this large integer. These are 3 large integers. And then I read the 2 numbers, integers from a command line, and multiply them together and print them out. And this is the result in the pink color. If you have access to a computer, a terminal, a Linux terminal, and if you have a calculator called a BC, type of BC and type these 2 huge numbers. It's easy to memorize. They're just going from a 1 to 10, and the second number is going the opposite way, and see if you get this result. Okay, so this example shows, in this case, the Fortran can handle these 2 large integers, but C cannot. In order to handle large integers and the large integer multiplication in C, you will have to do something extra. Okay. But this language, Fortran standard, does support a large integer and large integer arithmetic. Now, here's the Python and the Julia example. In Python, Python actually supports arbitrary position integers. So if you type 2 large integers, it will automatically use the right position to represent these 2 numbers, and then you multiply these 2 numbers. These are 2 huge numbers. It will give you this the answer, and you can check the answer by either looking at using the results using other language, for example, Julia, or you can again use the calculator BC to check your result. Okay. And the Julia, excuse me, Julia is also supports arbitrary position numbers. Now in Julia, it's not as elegant as in Python. You have to use the word big, and you use the quotes, double quotes, to represent a large integer. Okay. So next, so in order to correctly perform the large integer multiplication that we've just seen, in C, you can use a package called GMP. Okay, that's a multi-precision package, GMP, which is available for Linux, any Linux distribution and Windows as well, I believe, and Mac OS. Yeah, this open source package. So we use it as a GMP, and I use the data type defined in GMP, and we define the 3 variables, N1, N2, and N3. And then we use the GMP scanf, the input function, to input the first one and the second integer, and then do the multiplication. Now, notice here, the multiplications, those arithmetic operations, are no longer available for the operators. In other words, the operators are not overloaded. Of course, that's because the C, the operators cannot be overloaded. And you have to use the operations defined in GMP. For example, mul, add, div for multiplication, addition, subtraction, and so on and so forth. Okay. So using GMP, then you can do a large integer or operations. You can, because this is a multi-position or arbitrary position, you can do arbitrary position operations. On the right-hand side, we're using a package called the rprec, developed by the researchers at the Berkeley lab. So the rprec appears to be more elegant than the GMP, which is more a general purpose package. And rprec is more towards the scientific, and so more user-friendly to the scientists and the engineers. So you initialize the MP package, and you define the real, perhaps I should put the int as 3 numbers, and then you use the regular C++. By the way, this is C++ code here. And use the regular input and output operations operator to enter the 2 numbers, N1 and N2. Now, bear in mind, there's the drawback of this package is when you type a number from command line, somehow you have to type a comma at the end of that number from command line. And so far, this hasn't been fixed. That's a limitation. It could be it could disappear in the future, though. And then this operator, the nice thing is the operator is overloaded. The operator is overloaded, so you can carry out the operations as usual. Okay, so you don't have to write, you don't have to remember or look it up the what will be the appropriate the functions for desired operations. Okay, so function names and operators are overloaded. This is nice. So the languages that support arbitrary positioning arithmetic, here's a short list. BC, as just mentioned, that's a Unix command line multi-position calculator. If you have never used it, and definitely you should give it a try on your desktop terminal. Perl supports that, and the PHP is a language for web programming, and it also supports arbitrary position. Ruby, Haskell, and Python. Python supports arbitrary position in different ways. First, Python itself, at least the Python 3, supports arbitrary position. For example, if you just type a large integer, and it will automatically promote it to the right position to represent a number. Or you can use a package called MP-math. I'll come to this MP-math in a few moments. And with MP-math, you can do a lot more operations. Use the special functions, mathematical functions, the special functions, and the linear algebra operations with MP-math, which is very nice. And Fortran, and the Fortran standard has the select in and select real kind function. And these functions specify the range and the position that a variable of that kind can take. This is kind of nice, but it has its limitation because it will the actual position will be limited to the existing to the maximum range of existing floating point representation, for example, single or double or quad. Okay, it can't go and can't go beyond that. In so far, the Fortran standard is vague on this as to what position, whether it will support arbitrary position or not. The Fortran standard, by the way, the current Fortran standard is a Fortran 2018. Okay, so we do not call it Fortran 77 or Fortran 90, which is simply called a Fortran, and the current standard is a Fortran 18. And Julia, it's a new emerging language for high performance and productivity, and it supports arbitrary position, as we have seen. It can promote the numbers, the variables you define, and to the right, to use the right precision. Okay. A number of open source arbitrary position packages available. We just talk about the languages now. A list of packages are available. I just mentioned RPREC. This uses a 64-bit floating point arrays to represent the numbers. And it's a companion, MP Fun 2020. And also we have a QD at a quad double position. It supports both C++ and the Fortran. I should get rid of Fortran 90, just simply Fortran. And then we mentioned the GMP, and I didn't mention MPFR. And these two, the last two packages in particular, are useful. The MP Math, it's a Python package that supports arbitrary positions, and as well, it supports linear algebra, multi-position linear algebra operation, which is very nice. And for the compiler languages, MPAC is the only multi-position BLAS and the LAPAC library available for compiler languages. But it has only a C interface. It doesn't support Fortran directly. That's the limitation. For commercial packages, then people must be aware of Maple, Mathematica, that can do arbitrary position arithmetic. For Matlab, there are few options. Advampix, multi-position toolbox, and an experiment or toolbox by Crowley and Jeffrey from Western. For those who are interested, you can look it up, the paper published in 2009. Okay. And for some people in the community of using a multi-position, perhaps the multi-position BLAS and LAPAC and the special functions are mostly wanted. Now, one may ask, when choosing a package, you might ask yourself, does it have the interface to the language that you use? Or does it support operator function overloading? Because if it does, that would be very nice. You don't have to write extra code. And does it have a transcendental function implementation? Is it easy to port to the existing code? And these are the things you might want to ask yourself. As to go with GMP, MPFR, or RPAC, and the answer to that might be, are you using a C++ or Fortran? And what are you doing? How good are you at the languages? Are you really good at the C++? Or how much time do you have to write a code? That sort of things that you have to keep in mind when you make a decision what to use. Okay. Some notes on the key packages of potential significance. So RPRAC, it supports integer. It supports integer, real complex numbers for both C++ and Fortran. Intrinsic functions, operators are overloaded. This is very nice. So you don't have to write any the extra code. Once all the types of the variables are defined, then those variables will be automatically promoted to the arbitrary position you set. And the rest of the operations, the rest of the code can be kept as is. Okay. And its counterpart, MP-Fun 2020, which was just released before Christmas, supports same thing, supports integer, real, and complex numbers in arbitrary position. As most importantly, by the way, this is a Fortran only, and RPRAC is available for both C++ and Fortran. And MP-Fun 2020 is threat safe, while RPRAC is not. For those of you who have used RPRAC before and haven't touched it for a while, you might find that if you go download the latest version recently, 2.2.18, it won't compile. And this was fixed by my colleague, Paul Perini, just a few days ago, and he provided a patch. So the latest version now available since yesterday, I believe, is 2.2.20. So this patch compiles smoothly and can be used without any problem. The other two packages, MPAC. MPAC, it's a multi-position BLAS and LPAC library. It contains several hundred routines, but it has been inactive since 2013-ish. And plus, it doesn't have a Fortran interface. It has the simple, the interface, the same as the original BLAS and the LPAC, and it can be easily converted to, and a Fortran interface can be easily written. However, you still have to make an extra effort if you want to ever use it for Fortran. So that is a bit of a drop, unfortunately. And MP Math, it's a Python package. It supports the wide range of mathematical functions, and most importantly, linear algebra operations. This is really nice. Okay, so lastly, let's take a look at some more examples. So back to this broken curve, we know that if you go to GNU plot or Python, if you simply just plot this function and set the range from 0 to 40, you will see this phenomenon, okay? So here's the fix. In Python, I'm using a MP Math, import MP Math, and set the number of digits to 50. And then I plot this function. Okay, plot this function. Again, the plot this function, the red one is the broken one. The blue one is the one that is fixed. So it should go smoothly, asymptotically approaches 1 and going forward. The next question is, where does it break again? Where does this fix break again? So if you're interested, if you want to try, and if you want to send us your result and the reasoning, please do so by sending us an email to help@sharknet.ca and just say, hey, I found the answer where it will break with the 50 digits or whatever number of digits you want you use, and maybe you want to provide explanation why the curve breaks. Okay, if you're interested. Next, so compute the eigenvalues. Compute the eigenvalues. We're using the Wilkinson eigenvalue test matrix. If you're using a Matlab or you're familiar with this topic, and this is what the Wilkinson eigenvalue test matrices might look like. An n by n diagonal. It's an n by n tri-diagonal matrix with the diagonal elements defined in such a way. Here's an example. Example of order 7. We have the ones on the off diagonals, and if you apply the formula shown up here, you will see what the numbers on the diagonals are. And here, this is all number 7 or all of order 7. And this is what you should look like. You have a 0 in the middle and going from a 1, 2, and 3. If the n is even, you will see something different, okay? Just by this formula, by these two formula, when it's odd and when it's even. The reason that the people want to test or want to use this Wilkinson eigenvalue test matrix is to test the accuracy. This matrix has a property that the eigenvalues seems to come in pairs of identical values, but they are really not. Okay, so in order to verify this, we need a higher precision. For example, in a Wilkinson matrix of order 21, this is a frequently used case. After you calculate the eigenvalues, you will find the last two, as you can see, they look like they come in pair, like 2, 2, 3, 3, 4, 4, 5. And the last one, these numbers are really close. These numbers are really close, but not, the numbers agree to certain positions, but not afterward. Okay, this is for this matrix of order 21. So what if I'm looking at a larger number of a larger size? So here's an example in Python. We're examining the eigenvalues of this Wilkinson matrix of order 50. And I'm using the npmath library, npmath package. I set the number of digits to 40, okay? And I set the order size of the matrix to be 50. And I test whether it's an even number or odd number, and then I created this matrix, okay? You don't have to write these lines, then it can, you don't have to use the for loops. That can, these lines can be simplified using the Fortran. Sorry, it is the Python command, but just for illustration purpose, I wrote them out explicitly, so it's easy to follow. So I create a diagonal matrix. I create an array of a diagonals. Sorry, I create array elements on the diagonal and store them in D. And then I create a array of off diagonal elements, which is n minus 1, which has n minus 1 elements on off diagonal. And then I use the numpy to create this n by n matrix by adding these 3 diagonals together, adding the diagonal and 2 off diagonals together, and I will get a full matrix. You can try this. This is very easy to try. And then I simply call the function available in NP math eigenvalue, and this is also available, I believe, in the NumPy. But here, after I load NP math, import everything, and this the function name is being overwritten, is taken by the NP math library function, and then I just print them out, the eigenvalues one by one. So here's the full list of eigenvalues. As you can see, in the middle, there's a pair of eigenvalues, 20.5, and the digits after decimal points agree all the way until the very last, the third, very last. Okay. So you can imagine that when the size of this matrix increases, and you will, if you don't have enough position, if you use a double, for example, and you will get a result that show you have identical twin, which is really not. Okay, this is one of the reasons why we want to test the multi-position package using this Wilkinson test eigenvalue test matrix, just to see whether the two numbers are really equal or not by examining the number of digits after after decimal point. This one is in Python. The next one is in Fortran. So the right-hand side is the main function in Fortran. So we use the NP module, which is included in the NP fun. And then instead of using real or double, we're using the type NP real defined. We define the diagonal and off diagonal and some work spaces. And then we initialize the NP package by number of digits. I want to say, for example, I want 50 digits, 40 digits. And then we allocate the spaces. And then I created the matrix. I just omit that part for the simplicity. And then I need to call a linear algebra routine to compute eigenvalues. So the linear algebra routine that computes the tridiagonal symmetric tridiagonal matrices is called IMTQL1. This is a routine in the linear algebra package called ACEPACK. ACEPACK, by the way, ACEPACK is a predecessor of LAPACK, just for computing eigenvalues. Now, I would have to modify this routine a bit in order to make use of a multi-position. But fortunately, I only need to add 3 lines to change the 3 lines. First, I need to include a module. And the second, I need to replace the real declaration of variables with the TP, with the NP real type defined in NP. And the rest of the routine, I don't touch the rest of the routine. Nobody wants to touch this legacy code. This code, the algorithm was written in 1969, older than perhaps any of us. So with very little effort, only 3 lines in this case, I was able to compute eigenvalues to 60 digits or more. So here's the output. On the left-hand side, that it was using double precision. And then we see that we get a pair of identical twins. Because all the numbers, all the digits after decimal point agree with each other. Now, using 40 digits, we are able to find the difference after 38 digits after decimal point. This is why we're using a multiple precision, we're using more digits. Okay. The last example is the use of MPAC. MPAC is a multi-position BLAS and a LAPAC library. This, as I mentioned previously, that it has only C interface. So this is how it works. So what this example does is it computes the eigenvalues of a matrix. Okay. So what's happening here is we define, we allocate a space A for matrix and the W for workspace. Okay. Some of the, it is common that most of the BLAS and the LAPAC routines will use extra workspaces. So you need to pre-allocate the workspace rather than let the LAPAC routine allocate space for you. Mostly, as a matter of fact, they don't. So you need to allocate the workspace required by as an argument in the interface. So here I create a matrix, which is 1, 2, 3, the first line, and the second. Yeah. So I create a 3 by 3 matrix, and then I created the workspace, and then that's all. And then we call this LAPAC routine. This LAPAC routine has the same name as the LAPAC routine in double or real or double, a single or double position subroutine. The only difference is the leading letter R. In MPAC, the leading letter used in the LAPAC routines such as S for single, D for double, and the Z for complex replaced by R for real and a C for complex in MPAC. MPAC actually provides the interface to the LAPAC routine. And this is exactly the same sequence as the calling sequence as in the LAPAC routines. Okay. So after that, we will get the eigenvalues stored in those variables, and we will get the results back. It is actually quite straightforward if you get familiar with this. The only thing you need to worry about, the only thing you need to do is you need to replace the regular data types with the specific MPAC defined data types, and then that's it. Okay. Some summaries. Linear algebra operations, there seems to be only 2 viable options. One is the Python package, NP Math. okay? And for multi-position linear algebra operations, but it's Python. If you're not using Python, you cannot use it. And for the people who are using compound languages, Fortran and C++, the support for the multi-position linear algebra operations as provided in BLAS and LAPACK is still limited. MPACK is the only one, but unfortunately, it only supports C++ at the C++ at the moment. But on the other hand, it is not too hard to write a Fortran binding or Fortran interface, but there is a cost. You have to write some extra code. And the other thing I have to keep in mind, because the underlying key routines, the BLAS and the LAPACK routines are hard-coded in specific position. So there is no automatic mechanism that can be used to translate the target functions automatically. Okay, so this, in other words, there's no magic. Okay, you cannot just define the variables in your user's routines into arbitrary position and you call the underlying BLAS or LAPACK routine. That's not going to work. Okay. And for further readings, I just put a list of references over here, and I'll stop here. And we may take a couple of questions from the audience if there are any.